Classification of insecticides. Insecticides are classified in several ways, taking into consideration of their mode of entry, mode of action, and chemical nature of the toxicant. Classification based on mode of entry. Stomach poison. The insecticide applied on the leaves and other parts of the plants, when ingested, act on the digestive system of the insect and bring about kill. This type of poisoning is limited mainly to chewing insects. However, in sucking insects, feeding on plants up poisoned by application of systemic insecticides is responsible for the kill of the insect. The stomach poison should be palatable for the pest species and be able to bring about kill quickly. Control of another type is contact poison. The toxicant which brings about death of the pest species by means of contact with the wax monolayer and getting absorbed onto the surface of the cuticle of the body, and also that penetrates into the body through the vulnerable sites like sutures, membranes, bases of CTA and tracheal system on its body is said to be a contact poison. The stomach poison should be palatable for the insect species and be able to kill about it quickly. Contact poison. The toxicant which brings about death of the pest species by means of contact with the wax monolayer and getting absorbed onto the surface of the cuticle of the body, and also that penetrates into the body through the vulnerable sites, sutures, membranes, bases of CT and tracheal system on its body is said to be a contact poison. This is achieved by a direct application of the insecticide on the pest species, or by the pest species chewing or crawling or passing over the not chewing, crawling or passing over the treated surface having sufficient residue of the toxicant. Contact poisons are useful in the control of sucking insects. Fumigant. The toxicant, which in its gaseous state penetrates insect through the tracheal system and kills the pest species, is said to be a fumigant. All kinds of insects can be controlled irrespective of their feeding habits. In this connection, it is to be noted that certain compounds may have to be assigned to more than one group mentioned above. For example, lindane, though it is known as a contact insecticide, also shows stomach and fumigant action. Classification based on mode of action depending on the ways by which toxicant act upon the system of an insect to bring about its death. They are grouped as follows. Physical poison. The toxicant which brings about kill of an insect by exerting a physical effect is called a physical poison. Heavy oils, tar oils, etc. cause the insect, particularly scale insect, to die of asphyxiation by exclusion of air. Inert dusts affect a loss of body moisture by lacerating the epicuticle due to their abrasiveness, as in aluminum oxide, or absorb moisture from the body due to their hygroscopic nature, as in charcoal. Both the conditions may be found in certain dusts. Then protoplasmic poison. A toxicant responsible for precipitation of protein, especially destruction of cellular protoplasm of midgut epithelium, is said to be protoplasmic poison. Heavy metals such as mercury and copper, fatty acids, formaldehyde, ethylene oxide, nitrophenol, nitrocerol, fluorine compounds, arsenic compounds, etc. come under this group. Then respiratory poison, a chemical which blocks cellular respiration, as with the fumigants like hydrogen cyanide, carbon monoxide, etc., is said to be a respiratory poison. It combines with enzymes like cytochrome oxidase and other oxidases containing iron and thus inhibit their catalytic action. Nerve poison, a chemical associated with this solubility in a tissue lipoid and functions actively by blocking acetylcholinesterase in insects and warm-blooded animals, is called a nerve poison. Examples are organophosphatic and carbamate insecticides, organochlorines, DDT, lindane, paradichlorobenzene, etc. Botanic insecticides, pyrethrum and nicotine, etc. Poisons of a more general nature or action. This category include compounds which induce neurotoxic symptoms after some latent period. Chlordane, toxaphene, aldrich, and dieldrin. those which have an immediate depressant action, organic thiocyanates like thionite, and which are muscular depressants, rotenone and phenothiazine. Then, so this classification based on mode of action: physical poison, protoplasmic poison, respiratory poison, nerve poison, poisons of more general nature or action. Classification based on chemical nature. The following is a broad classification of insecticides: rodenticides, nematicides, acaricides, and molluscicides based on their chemical nature. Two major divisions: inorganic compounds and organic compounds, are recognized. Inorganic compounds: arsenic compounds, fluorine compounds, sulfur and sulfur, barium carbonate, thallium sulfate, and zinc phosphate. Organic compounds: hydrocarbon oils. The constituents of the oils are solely of hydrogen and carbon. Two groups like mineral petroleum oils and coal tar oil is recognized. The mineral oil or the petroleum oils are derived from the sedimentary rocks. Kerosene, lubricating oils, tars, asphalt, other mixtures are derived from them. Among coal tar oils, creosote oil and green oil or anthracene are useful for insecticidal purposes. Anthracene oil is used for wood preservation. Use of oils in pest control has assumed importance since 1874 with the discovery of kerosene, soap, and water emulsion. Oils in their natural state are phytotoxic. However, they find use as solvents or dilutants for chemical toxicants. Their insecticidal activity is attributable to the presence of certain fraction of heterogeneous mixture of saturated and cyclic hydrocarbons in them. Advantages of oils are relatively cheap, good spreading capacity, low toxicity to animals, easy to mix, and non-development of resistance in insects to them. Disadvantages of oils: low toxicity to insects, instability in storage, phytotoxic nature, and injury to parts of spray such as rubber hoses. Then animal origin: a toxin isolated from the marine annelids Lambertensis heteropoda and L. breviserae has been found to possess insecticidal properties. The toxin is known as nerexotoxin, 4-NN dimethylamino 1,2-diethiolide. Various kinds related compounds have now been synthesized, and most of insecticidal compounds have been noticed to belong to the group of 2-NN diethylamino 1,3 propane dithiol esters or 1,3 dithiol esters. Of this, 1,3 bis carbamoyl thio 2-NN diethylamino propane hydrochloride has been observed to effective as an insecticide. It has been found effective against rice stem borers and cabbage diamondback moth. Plant origin: nicotinoids, pyrethroids, retinoids, other plant products, and volatile oils from plants. Synthetic organic compounds: organochlorines, organophosphorus compounds, carpamains, organic sulfur compounds, synthetic pyrethroids, dinitrophenols, thiocyanates, other miscellaneous organic and fixed oils and soaps. Next topic, somewhat related to this topic: synergists, also called activator or adjuvant. The term synergists derived from the Greek word synergos, meaning together. Synergists are chemicals which have little or no insecticidal activity of their own, but when added to an insecticide, enhance its toxicity manyfold. The enhanced toxicity is greater than the sum of the toxicities of the two components used separately to more than the additive total toxicity of the two taken together. This phenomenon, first discovered in 1938, is known as synergism, and the substance producing a synergist, a substance that has the opposite effect that which reduces the toxicity of an insecticide is called an antagonist. Example of synergists. Synergists are known for only some insecticides like pyrethrins, rotenoids, and certain organophosphates. The best and first known synergists are those relating to pyrethrins. Pyrethroid synergists fall into three classes of chemicals: methylene dioxyphenyl compounds such as sesamine, derived from the oil of Sesame indicum, so piperine, obtained from black pepper, then piperoyl cycloine or cyclohexone for field crop insecticides, piperonyl butyroxide, good for livestock insecticide, piperoyl amides, propylizome, and fagaramide. N substituted amides like N-isobutyl decylamide or N950, and terpene derivatives like thanate, terpene diacetate, and pine oil. Some of these synergists are also the synergists for organophosphate, for example, pyrronyl cycloine sulfide, pyrronyl butoxide, pyrronyl isome are good synergists for comaphos, and pyrroyl butoxide and sulfoxide for diazine. Then pseudosynergism. Certain substances increase the efficiency, not the toxicity, of pyrethrins by stabilizing the droplet size of their spray, and this ensuring better and persistent contact with the insect body, achieving a better rate of killing. They are defined to be the pseudosynergists. Examples are teic acid, lubricating oils, and the oil part of the sesame and pine oil from which sesame and the actual synergid has been removed. Mode of action. The mode of action of synergists has not been clearly understood. Three possible mechanisms are suggested. Synergists may produce two types of effect. They activate enzyme system, which then enhance the toxicity of the insecticide. This is a slow process taking a long time to operate, therefore not useful for synergists. Non-inducible effects are those which synergists inhibit the enzyme that toxicates the insecticide and this enhance the killing power of the later. Synergists may improve penetration of the insecticide through the insect cuticle and the nerve system. This is indicated by the fact that synergism occur only when application of the synergid prioritises that of the insecticide. If the synergist is applied later than the insecticide, no synergism is seen. Synergists may be protecting the insecticide from withering effects, thereby increasing the residual action and thus the amount of kill. Some common mixed formulations in use in methylparathion plus DDT, toxaphene plus DDT, carboxyl and gamma BHC, methylparathion, carbaryl 1:4, and pyrocan E220, etc. The advantage of mixed formulations of insecticides are that the mixture is more effective due to synergistic action. There is saying in the effective control operation, it is believed that mixed formulations having independent joint action may tend to prevent the development of insecticide resistance in plants pest species, and it is possible to control resistant strains of insect. Examples are DDT resistant flies and controlled by Daikin and DDT methoxyzole combinations. Next topic, fumigants. A fumigant is a chemical which at a required temperature and pressure can exist as a vapor or gas that when released penetrate objects or enclosed areas in concentrations that are lethal to pest organisms. This definition excludes aerosols, which are particles suspended in the air, which are often referred to as smokes, fogs, or mists. Fumigation technique has great adaptability in pest control. They can be used to control wood destroying insects in structure and furniture where liquid or dust formulations are ineffective. or where these materials may cause damage. Under some conditions, fumigants can be applied to control burrowing rodents that can't be reached with other types of rodenticides. Most commonly, fumigants are used to control insects, weed and disease control in soils. Commodity fumigations for insects in fresh and stored food products such as grains, fruits, vegetables, nuts, and dried fruit and ground burrowing rodent control. So, fumigation technique have great adaptability in pest control. They can be used to control food destroying insects in structures and furniture where liquid or dust formulations are ineffective or where these materials can cause damage. This is a vapor or gas. Okay. And we are excluding smoke, fog, mists. Under some conditions, fumigants can be applied to control burrowing rodents that can be reached with other types of rodenticides. Most commonly, fumigants are used to control insects, weed and insect control in soils. Commodity fumigations for insects in Most commonly, fumigants are used to control insects, weed, and disease control in soils. Commodity fumigations for insect and fresh and stored food products such as grains, fruits, vegetables, nuts, and dried fruit, and ground burrowing rodent control. Limited fumigations take place to control infestation of food destroying insects and in structures. So, before performing a fumigation, the applicator needs to understand clearly the hazards and problems associated with the use of fumigants. Most fumigants are highly toxic to all forms of life, including human, animal, plant, and even microbe. Fumigation is highly specialized operation that require equipment, technique, and skill, not generally used for applying other types of pesticides. Applying a fumigant may be time consuming and expensive, usually requiring more labor than other pest control methods. Mechanism of action: fumigants killed by interfering with the respiratory function of the target pest. The gas enters the larvae, pupae, and adult of insect through the spiracles and egg through the chorion. Molecules of some fumigants, for instance carbon dioxide inert gases, replace oxygen molecules in the air so that pest control action involves smothering or asphyxiation due to lack of oxygen. The killing action of a fumigant is influenced by its concentration in the atmosphere, the length of time it stays in the atmosphere, and the temperature and humidity of the area of the time of fumigation. Fumigants are designed to enter cracks, crevices, and other areas where target pests may occur. They may be applied in enclosed areas. Fumigation has no residual effect. Reinfestation may occur after the fumigation has diffused from the area. Advantages of fumigation. Fumigation has several advantages over other methods of pest control. Fumigants are usually quick acting and can result in total eradication of the pest. Because fumigants are gases, they diffuse through all parts of the structure or commodity being treated and can reach pests that cannot be reached with conventional pest control materials or techniques. For certain commodities, fumigation is the only practical way to control pests. Single treatment only kills most pests in treated area, toxic to a wide range of pests. Disadvantages of fumigation. There are several reasons why fumigation sometimes may not be the best means of pest control. The control achieved through fumigation is temporary. There is no residual action from fumigants. Where untreated populations of pests remain, reinfestation of the treated site can take place quickly. Fumigants are toxic and often highly hazardous to the applicator, requiring special precautions during application. Fumigants must be retained in the gas form for a period of time to be effective, often calling for extra supervision. Fumigation must never be done by just one person, which require added labor. Some commodities or pieces of equipment may be damaged by certain fumigants and must be removed or otherwise protected. Fumigant activity may be greatly affected by temperature and humidity. Examples: methyl bromide. Methyl bromide has been used as a fumigant since the 1930s. It readily penetrates many materials and it is in wide use for structural space fumigation. Methyl bromide is also used in agriculture as a soil fumigant to control fungi, weeds, nematodes, and insects. So, methyl bromide has been used as a fumigant since the 1930s. It readily penetrates many materials and it is widely used for structural space fumigation. Methyl bromide is also used in agriculture as a soil fumigant to control fungi, weeds, nematodes, and insects. Methyl bromide is one of the only fumigants registered that can be used on shipments of commodities that must meet restricted agricultural quarantine regulations for most countries. Methyl bromide is effective against a variety of pests, including hitchhikers, and can be easily and economically applied to both small and large shipments. Then chloropicrin. Chloropicrin. Chloropicrin volatilizes to form a dense gas that is about 5.7 times heavier than air. Chloropicrin is highly toxic to insects, vertebrates, and many soil microbes such as fungi. It is also injurious to plants even when used as a warning agent in other fumigants. It is highly irritating to eyes, and it is a powerful tear gas. Which one? Chloropicrin. Concentration as low as 1.0 per part per million ppm cause intense eye irritation, and prolonged exposure cause severe lung injury. So chloropicrin can cause severe injury upon skin contact. Uses of chloropicrin on food stuffs is prohibited due to adsorption potential. Chloropicrin. Then phosphine. The aluminum phosphine reacts with atmospheric water to produce hydrogen phosphide gas. This gas is also known as phosphine. Phosphine is a colorless gas with an odor that smells different to different people. The odor is often described as similar to garlic, commercial carbide, or decaying fish. It is highly toxic to all stages of insects, although requiring 72 or more hours of treatment time. Pre-adult stages of some insects are resistant to short exposure to phosphine gas but are controlled by a 10-day or more fumigation period. Hydrogen cyanide or HCl. Hydrogen cyanide was one of the first fumigant to be used extensively under modern conditions. Its use for treating trees and tents against scale insects was developed in California in 1886. The use of hydrogen cyanide has been declining in recent years, but it is still important in certain fields of application. Hydrogen cyanide is one of the most toxic of insect fumigants and may be absorbed through unbroken skin in toxic amounts. Absorption increased if skin is moist. The fact that it is very soluble in water has considerable bearing on its use in practice. Thus, it may produce injury on moist materials such as fruit and vegetable because the solution of HCl in water is dilute acid. Methods of fumigation. Sprinkling. Fumigants can be sprinkled on top of stack as it is done in case of AD-CT mixture, which is heavier than air, or chloropicrin on the floor of mills with water sprinkling can. Open space method. It consists of forcing fumigants into the open space of the enclosure through a conveying system consisting of metallic tubes, as is most commonly done with the flour mills in the United States. Fumigation with hydrocyanic acid liquefied under pressure. The large open space of mills or in mills consisting of more than one floor, the fumigant is conveyed to the well-sealed open space of the interior of the mills. The well-laid-out piping system having nozzles fitted at convenient locations. The liquefied fumigant or gas is forced into the space through manifold inlet of mill, and this forcing in of fumigant is aided by air compressors. Then pot method. In this method, the gas is generated in earthen wire jars or paraffined barrels kept within the enclosure to be fumigated. The liquids that are vaporized at ordinary temperature, like ethylene dichloride, carbon tetrachloride, ethylene dibromide, are amenable to this method of fumigation. Solid fumigants like cyanides of alkali metals are also fumigated in this method. Here it is done by mixing water and sulfuric acid in the pot and adding required quantity of cyanide of alkali metal say sodium cyanide when the mixture is hot by chemical reaction. As heat is gathered by the reaction of water and acids, the pot should be strong enough to resist cracking. In order to avoid accidental spilling of the acid, and pots may be kept in open boxes. Unimpregnated discoids. In this, the liquid or liquefied fumigant absorbed in the inert material will be pressed into water like wafer-like discoids, each containing non-quantity of fumigant. Zyklone discoids are example of fumigation of hydrocyanic acid used for fumigating small mills. The discoids should preferably be kept on paper to avoid damage to floor and other objects by acid oozing out of the discoid. To check quick liberation of gas from discoids, it is advisable to chill the container before opening it. Spraying of fumigants. This is more or less than sprinkling, but it is done by means of sprayers for liquid fumigants for further facilitating the evaporation. Dry method. Pellets, powders, and tablets of quite a few fumigants are available. These contain measured quantities of fumigants and may be placed at required intervals in space and introduced into holes and then sealed. Such tablets or calcium phosphide and powders of calcium cyanide are available. No special device is required for liberation of gas. Both calcium phosphide and calcium cyanide liberate phosphine and cyanide gas respectively by the moisture of atmosphere when kept open. Ampules. Some fumigants like ethylene bromide or dibromide are available. Ampules containing non-quantities of fumigants. These are used to fumigate bulk storage where the required ampules are inserted within the bulk of grain in a gas-proof sack and then mechanically broken which under ordinary temperature generate gas. Hazards of fumigation. Harmful effects from exposure to fumigant may fall into two major categories. So methods: sprinkling, open space method, pot method, impregnated discoids, spraying fumigants, dry method, then ampules. Hazards of fumigation. Harmful effects from exposure to a fumigant may fall into two general categories: acute and chronic. Acute effects can result from a single exposure to high levels of fumigant, with symptoms generally appearing within a few minutes or hours. The symptoms vary with different fumigants, and different individuals may be affected differently. Chronic or long-term effects may result from an overdose of a single exposure on a single exposure to a toxic gas or from exposure to low levels over a period of time. The effects may not appear until long after exposure, and in some cases they may not be easily associated with the poison. It has been demonstrated that certain of the fumigants can produce cancer in test animals under experimental conditions. Most reactions to fumigant poisoning differ from those of exposure to other pesticides. For instance, many fumigant reactions stimulate drunkenness, slowed body movement, slowed speech, dizziness, numbness to hands or feet, coughing, sneezing, dryness, irritation of nose and throat, breathing difficulty, nausea, abdominal pain, serious eye and skin damage. General precautions. General precautions for the handling and use of all fumigants may be considered under four main headings. Preliminary, those taken during application, those taken during the exposure period, and post treatment. Preliminary precautions. Under this heading may be listed advanced precautions for a more general or permanent nature, and also preliminary measures applying specifically to each fumigation job. In any fumigation, large or small, no person should work alone. Because poisonous gases are being used, serious consequences may ensure if a fumigator becomes sick or faint and it is unable to finish to control the operation. No matter how small the dosage or the scale at work, at least one other person should be present in case of emergency. Then precautions during application. In addition to proper respiratory protection, sculptors' care should be taken to ensure that fumigant formulations or liquids do not come into contact with the skin. If clothing or footwear become contaminated, it should be removed immediately and affected areas of skin washed through thoroughly with soap and water. Precautions during exposure period. Every precaution should be taken to avoid exposure to escape fumigant and to prevent unauthorized entry into treated space. Warning signs that indicate the type of fumigant in use and the date of treatment should be put in appropriate places. Then they should be removed after the treatment is completed. Pre-treatment precautions. Post-treatment precautions. After adequate aeration of the treated area, gas detection equipment should be used to ascertain that all fumigant has been removed. As the process of desorption can vary greatly with the different fumigants, different commodities, and different environmental conditions, precautions should be taken to ensure that harmful levels of gas do not subsequently accumulate where personnel could be exposed.